Hello, everyone, and welcome to the beginning of our conversation on chemical kinetics. So up until now, our focus has been exclusively on chemical thermodynamics, which is essentially saying that in the long run, what does their chemical system want to look like? So for example, it turns out that your car, and pretty much any iron, eventually wants to oxidize, and eventually it'll get there. But here's where the real fun of life and chemistry happens is it's much more about how long something happens. So one of the important things to think about when we think about life is we are just a giant sack of unstable molecules that kind of wants to combust and burn into flames. But here's the trick about life is that we make sure that all of those combustion reactions happen slow enough that we're kind of just the physiological version of a car engine, constantly exploding, but using that energy to keep us driving forward. So, the whole point of this is that the rate at which chemical reactions occur can vastly control the system and the dynamics of how a reaction and system behaves. So, one of the things I want us to really focus on as we go forward is not just where systems want to be, but what sort of path it's going to take for us to get there. So, one of the things that's important to remember is that for a reaction to occur, it needs to be both kinetically and thermodynamically feasible. So, it doesn't matter if something is thermodynamically feasible, such as turning graphite or diamond into graphite, if it's kinetically impossible. So, we now know how to address the thermodynamics portion. We're going to go ahead and try and focus a little bit more on this kinetics portion. Now, one of the other important things that's really important to keep in mind is that real systems and real reactions are really messy. So, one of the big points that we're going to try and do is focus in on elementary reactions. So, this is single step reaction mechanisms where A plus B goes to C plus D. So, this is essentially as stripped down a reaction as I can get, where there's no intervening steps. The molecules are actually coming together. So, a good thing to think about when we're thinking about elementary reactions is our good old friend organic chemistry. Because when we're doing an organic chemistry mechanism, we're really kind of plotting out exactly in what order A and B have to come together to eventually get us the products that we want. So we're going to try and focus in on this elementary reaction portion. And one of the nice things about these elementary reactions is that they only assume a forward reaction mechanism. So they assume that this entire reaction goes forward, but there may be another elementary reaction which reverses the whole process. So the general goal of this chapter is going to be to build up our understandings of elementary reactions and use them to try and decipher what an overall reaction mechanism looks like. So, how these individual elementary reactions kind of couple together. So, we'll be dealing a little bit with elementary reactions and a little bit with the more general form. So, a category that kind of belongs in both is our actual rates of reaction. So we can examine these for elementary or overall reaction mechanisms. So once we have this reaction, if I want to know how fast this reaction proceeds, we're going to need to associate a given rate to this reaction. So how we're going to define the reaction rate is essentially how many equivalents of reaction occur per unit time. So the change in the extent of reaction versus the change in time it takes to accomplish that. So a classic version is moles of reaction per second or moles of reaction per minute or per hour. So one of the things to watch out is that there's a lot of different conventions depending on the reaction you're examining of which basis for time you're going to use. So make sure you pay very special attention to our units for this. So we can actually relate our rate of reaction to the actual change in moles of each of the individual components, making use of our reaction coefficients. So these are our good old reaction coefficients from Gen Chem that we've dealt with so far. And again, I do apologize for the use of multiple V's. Here, V sub A is going to indicate the coefficient, whereas the general V uh, is going to indicate the reaction rate. I'll try and point it out if this notation differs. So what we can do is say that if I know that 1 mole of reaction occurs, say every minute, I can use this to relate with how many moles of product are going to be formed. So if the reaction proceeds, my rate of product formation should always be positive, and we're going to use uh, signs that essentially reflect this. However, for every 1 mole of reaction, there's going to be VC of C being formed. So in this case, in order to set these two equivalent, I'm going to essentially divide the rate of production of each of my products by their coefficients to scale down to how many moles of a reaction have occurred. So using this notation, it's easy to go in between moles of product formation and moles of reaction occurred. And we can do a very similar thing dealing with reactants. The biggest difference here is that reactants will show a negative rate. Again, a negative or a decrease in the amount of reactant present indicates a positive reaction rate. So again, do watch out for the signs as well. Now, one of the other things to watch out for here is, again, we're focusing in on moles of reaction per time. That means we're in size extensive units. And as we've seen before, size extensive units are fairly annoying as they do highly depend upon the exact system that I'm studying and aren't quite so universal. So we're often going to want to turn these into size intensive units. So one of the things you should watch out for is what uh, size extensive property we're going to use. So for solutions, the typical notation is to put it in molar. So essentially how the molar concentration changes per time. And for gases, it's how the pressure changes with time. However, it is worth noting that some exotic systems will use some other notation, such as you may see surface areas um, or density changes or other things for more solid-based systems. However, let's say that I have a solution-based system and I want to bring it into units of molar per second. Well, I already have moles per time, so all I need to do is divide the system by volume. And here's where we actually get really lucky, because since this reaction all occurs in a single container, then that means that they will all share a volume. So this volume term will be consistent for the whole system, which is going to uh, help express the system, and also makes it so that I can relate the change in the number of moles of C, D, A, or B with volume as simply the change in concentration. So I congratulate you. We've now reached the second time in all of physical chemistry where we're going to be dealing with units of molarity. So this can join osmotic pressure on our pedestal of where molarity actually matters. However, it's also easy to see how we can translate in between molarity and pressure as long as we know the temperature of the system and, again, assume ideal gas law. So now what we have is a way to convert the changes in concentration of any of the chemical species present in solution to the actual rate of the reaction. And we're going to be making use of these relations quite vigorously throughout the rest of the unit. However, one of the other things that's worth noting is that we still have yet to decipher a way to actually determine the rate of reaction. And what we're going to try and figure out is what controls we can place on the rate of reaction on the system that will control the rate of reaction. So one of the easiest ones to kind of notice is that the reaction is going to will tend to be dominated by the frequency at which the reactants come together. If my two reactant molecules never meet, I wouldn't actually expect a reaction to occur. And so what we're going to need to do is often very empirically try and figure out what sort of concentration dependence our rate of reaction will have. So we're going to be, again, looking at how frequently A and B will come together to form the product species of interest. So because we know there's a concentration dependence, what we're going to do is for a elementary reaction, we're going to assume that the reaction rate is going to depend on the concentration of A and B, both raised to the power of how many molecules are actually going to be colliding, which should be controlled by the stoichiometric ratios. And again, Kr is just going to be our rate constant. So it's going to help us go from the actual controlling uh, rate concentrations to the essential rate of formation. So in order to, and unfortunately, this parameter is going to be largely controlled by the sheer nature of the reaction and often needs to be determined empirically. So we're also going to run into one last little problem. And this is the fact that most of our reaction rates aren't going to correspond to elementary reactions. So I have to deal with the fact that I can't just assume that if my overall reaction involves, say, 3 moles of A and 2 moles of B, that I'm going to see a similar dependence on my order of the reaction, where I'm going to have A to the third power and B to the squared. Unfortunately, what there's often going to be is an elementary reaction somewhere along the way that's going to essentially slow down the system. So a good place to start when trying to determine rates of reaction is trying to figure out how I can more empirically determine A, my rate constant, and B, my order of reaction. And we'll go ahead and address that pesky little issue more next time. Until then, take care.